Good morning, good afternoon, good evening, everyone. This is Bonnie Crossland. I'm the product manager for gas chromatographs for Emerson. And today we're going to be doing a webinar on the calibration gases and how to calibrate a GC correctly. So most of this information will be applicable to anybody's GCs, preferably online GCs. There will be a few sections that relate to how you would do it with an Emerson GC, but I am pretty confident that it would be a similar process if you had a different GC than an Emerson one. Because we do this webinar is multiple time zones, and 10 o'clock a.m. Houston time is not convenient to everybody, this presentation will be recorded. Those who have registered, whether they're attending today or not, will receive an email with a link to a copy of the webinar once it's completed. It also will be uploaded onto the Emerson sales site or external website so that it can be futurely downloaded or viewed. And so with that, we will get started. Just a few basics we're going to go through for those who may have not attend last month's response factor webinar. So on your screen, you should see a presentation window. You should also see a Q&A window, and if you notice, there was no call-in, so there's no way to actually verbally give me questions. So everything will be need to be submitted through this Q&A window. If you have any questions, we will try to get to as many questions as possible. Last month's webinar had about 46 questions. We could not get to them all, but we will try as much as possible during this webinar. Below the Q&A box is the speaker bio. Below that is related resources. There's actually 2 resources for this. Unfortunately, one of the team members who has access to upload resources is sick, so he was not able to upload the resources, but we will have a PDF copy of this presentation, as well as a resource that lists basically the calibration standards for a C6 Plus and a C9 Plus. So we'll make those available after the webinar for you guys. There's also the ability that if you want future information or contact after this webinar ends, or if in the future that you are hearing this on playback, you can send us an email and we can answer your questions. We can also have a salesperson contact you regarding a specific problem you're having or a specific interest in a GC. And again, this is streaming audio. We do want to mention that there's no call-in number. So if you do need to have this, if you need it verbally, you need to basically make sure your computer's unmuted, as well as you need to make sure that your Adobe Flash is working. I know last month for the response factors webinar, there was a bit of a problem with some of the audios. So I will start going into the presentation. This is what we're looking to cover. So just choosing the calibration standard, followed by just a quick overview of the calibration standard certificate, things that are on it that are important for you to familiarize yourself with. And then we will go on into how to auto-calibrate. Now this is focused on how to do it the Emerson way, using an Emerson GC, but again, it would be a similar process for the competitor GCs as well. Then we talk about manual calibration, and this is mostly used with liquid standards, but it can also be used with the gas standards. And then there's a few little tweaks within our software, some options that you can select. And finally, we will try to get as many questions as possible answered. If we are not able to get to all the questions, they will be uploaded with the answers onto the Emerson website. We can also then as well individually answer those emails. We do get a copy of all the questions that were submitted with a way to contact the submitter back with the answers. But a lot of times we do like to share those questions with everybody, because generally if one guy is asking the question, 3 or 4 other people have that same exact question. Excuse me. So we're going to start off with a quick poll. And basically the question is an appropriate calibration standard and proper calibration method important? So it's kind of a probably already an answer that you guys should be familiar with, but I'll let you guys answer the poll for a few seconds, and then we will move forward into the production. So pretty much correct. So I'm glad that nobody selected the third answer. One, because repeatability actually incorporates accuracy into the number. But correct. Actually, it's answer 1 and 2 are correct. It is a comparative message. That's why your calibration standard is so important, because you are comparing how your performance on the calibration standard to when you're actually measuring the stream. And most of everybody got 80% correct, said that yes, the GC is as accurate as the calibration standard that it used. And so with that, we'll further move on into the presentation. So hopefully this comes up. Okay, so basically we kind of answered the questions, but get the most accurate calibration gas available. So generally they're on the market as 1%, 2%, and 5%. For natural gas applications, that is what we're basically thinking of: C6 plus, C9 plus, C7 plus, things basically generally more along the pipelines. We really do recommend a 1% tolerance calibration. It's really only a small differential. When we did a quote, it's about $58 in delta. And on the next slide, I'll show you what that $58 different delta can actually end up costing you and loss and unaccounted for. Now, when we do other gases like custom applications or liquids, 2% is fine. There's no reason to get the extra 1%, basically because in those cases it does get quite more expensive than it is when you do it with a standard one, that like a C6 9 and a C6 plus. And that is what we generally in-house we use will be a 2% for our process applications or any of our liquid streams. So I just want to quickly show you how basically on a pipeline application, C6 plus, that 1% accuracy can actually make a big difference. And so this is a calculation that was done actually for a particular class, but in this case, what I'm assuming is we have, in the first column is generally our particular calibration standard that we get for a C6. And if we just was running high on the methane, say 1% accuracy on the high end of the specification, and then in the third column, if we were running at 2% on the high end from the basically nominal value, and then then I normalize those values. Well, there's not a really large difference in the BTU value calculation. It's really small, right? 0.33 BTU. When you work out the math, so I took the gas prices that's been running lately, $2.83, and I times it by, say, a given flow rate, and this is a moderately to high flow rate. You can see that on a daily basis, the difference in accuracy is about $1,700. And so while that may not be the biggest number in the world, Jordy, by that just that slight variation in accuracy way overcompensates the $58 in the two calibration standards. And if you times it on a yearly basis, it's basically over $600,000 differential in loss unaccounted for just by a 1% differential in the calibration factor. So that 1% can make a really big difference in this case when you're operating as a cash register. So that is why we often will tell you for the standard natural gas applications, especially like I said with the cash register, that 1% difference in the standard can make a big difference overall for the year. So I'll go forward. So calibration. So if you want to know what the calibration standard is, so the example, the one I just showed you is one that we recommend for a C6 Plus. These standards are published, they're in our manuals, but we also have a product notice that we have sent out. That is one of the resources that we're going to make available. So I'll bring the slide up. And this is basically our recommended standards and what we use inside Emerson for our C6 Plus and our C9 Plus. I don't expect you guys to memorize this, so this is available. We will provide it for you. And just as an FYI, the reason we do 2,dimethylbutane is actually for valve timing. So it's not a component we technically look for in the C6 application, but it gives us a little bit easier valve timing. And that's something that to think about when you do pick a calibration standard. It doesn't necessarily have to be everything that you're looking to measure. Sometimes we add a little bit extra to help us with valve timing. Now, when we do the calculations, we do add that with the N-hexane for a C6 Plus number. So this is actually the product notification I mentioned. This was supposed to be one of the resources. So if you guys need a copy, again, we'll be putting it on the Emerson external website, but if you don't want to wait for that, we can email you a copy of this product notification at analyzers@emerson.com. So I'm seeing a lot of questions that people are either not seeing the slides move or they're not hearing the audio. So I'm going to move a little bit forward, and then I might need to take a few seconds out to answer some of those questions so that people can catch up to where we're at. So the number thing too is if you're not getting a natural gas application and you're getting more of a process or kind of say maybe an LPG type of application, what we do with every GC that we send of that nature, we will provide what we consider a parameter sheet. And with that sheet, we will actually tell you what the calibration gas that we are using is. So this is an example of the parameter sheet that we would make available for you for your custom GC. And basically, if you can look down, it's kind of a little small on my screen, but it's the Cal standard data. And that is where the calibration specification that we would purchase and what we would supply and what we're going to test your GC to. This is an FYI. This cover sheet would actually be completed out. But for confidentiality reasons, I have cleaned out the sheet. This would all be filled in as well as the other tabs. But just like I said, for confidentiality, not to share information into for other people, we've kind of cleaned that all out. So let me show you what a parameter sheet would look like closer up. So in this particular case, off the application data tab, this would be what this individual is particularly looking to measure. And so below it, you'll see in the baby blue is what we would get to order as the calibration standard for this particular application. And you'll notice that we tend to take the normal values in the mid-range. So in this particular case, so this isn't a gas calibration. You can tell by it says vapor, but we pick the mid-range as what they think the normal is. So we wouldn't necessarily pick the max or the min range, but what you is normal, because we want to be as most accurate as we can on what you think you're going to see through your stream. Same thing, this one's a liquid. Again, we picked basically the normal value. And generally it's the things that we're going to measure unless this was like in a base of something, and then we would, even if say this was in a hydrogen base or methane base, even if we were not measuring that, obviously we would have the balance be that. So in this particular case, C5 is the base, but we're also looking to measure it. So again, this is kind of how it lays out. This will be in every custom application GC that we do. We will have the parameter sheet that provides on the last tab the calibration standard that we've used to test your GC to. So also, just because I know we do have a few calibration standard companies online, you can call them as well. They are your experts, and this is what they do for their business, and you can call them and tell them what you're looking to do. A real-life application is that right now we're working with a company that has to comply with EPA rules, and so they have to do calibration at 3 points, a low, middle, and high. And so one of our recommendations for them is to validate with the gas supplier, standard supplier, basically, what's the recommendation of how these 3 gases have to work together, because they do have certain rules per the EPA that the GC has to pass, and how the calibration standards have to be mixed. So that's another resource you can use as well. The one that I just want to add is that while we definitely try to be the normal value or the expected value, we do need to look at it for reasonableness. Sometimes we can tell they were auto-generated numbers, and it really will make us either a vapor or liquid standard that's almost impossible to maintain, and so we will make an adjustment when we needed to do that, but generally we do pick the normal values. So before I go on to the next section, I think there's a couple of unanswered questions. So let me just spend a few, pick one here. Is there an ideal range for each component for a good calibration? So yes, so the ideal range, or it says range is basically the normal value expected, right? So it's going to vary depending on what somebody's application is. So if you think your range is 20 to 40 is going to be your normal range, we would say then 30 would be our target for the calibration gas. Now sometimes what we may do, if you have a low detection limit something, you say you're going to range from 3 ppm to say 50 ppm. While the average may be somewhere around 25 ppm, we actually might run 2 calibration standards, one around the 25 ppm range, but also one down at the low end, closer to the 3 ppm, because we want to make sure that's an important detection range for you that we can detect down that low. So sometimes that is something that we will do. Another question we have is, isn't it better to make a calibration standard as close as Isn't it better to make the calibration standard as close as the process gas that will be measured? Correct. So when we rely on you to tell us what is going to be measured or what you expect the range is. Again, in my previous example, if it is you're looking for some low detection limits, we may actually use 2 calibration standards, one in the moderate range or the middle range of what your expected values to be, as well as if it's a low end, make sure that we can detect that low end as well. What is the C9 plus recommended composition for the cal gas? So we will make that available. I'm not going to go back and read that out, but we can make that product notification available for you guys. It will be available externally, but you can also contact us at Emerson, analyze@emerson.com. What is the standard to use nitrogen as a carrier gas for GC? So using nitrogen as a carrier will depend on the application. We often use it when we use a FID as a detector. You'll see nitrogen is very often used as the carrier but it really does depend on the components being detected. We wouldn't use nitrogen for a C6 or C9 application because nitrogen is one of the components you're looking for. So it really depends on what the detector is and what are you looking for. The thermal conductivity detector, obviously using nitrogen as the carrier when that's one of the components we want to detect isn't going to work, or if its thermal conductivity is close to one of the components you're trying to detect, we would not use it as well. Okay, there's definitely a lot more questions, but I'm going to just kind of move on quickly. Otherwise, we'll be on a 3-hour webinar. So this is basically what a calibration standard certificate looks like. Now, obviously, I did cut off the top portion that lists the PO and the serial number and the part number. We've cut that out just because that's, for this particular example, is not what's important. But we do want to show when you have this left-hand side, the box I have circled, that is the components that we are looking to measure or are of interest. So we want to make sure when we get the certificate that everything we ask for is listed. If it's not, then we need to talk with the standard supplier. 2, we want to make sure that the certified concentration is what we've requested. So if we have the parameter sheet out, we would compare that to make sure we got what we asked for. This is also important because these are the numbers that are going to go into your component data table, and they're then later used to help determine the response factors. So this is important, but these are what you expected. And then this column, the last column on the right, is the accuracy. Again, for natural gas applications, we do target 1%, but for our process applications and our liquids, we do target 2% is really fine. Otherwise, it can get really expensive and you don't get as much bang for your buck as you do with the natural gas applications going for a tighter tolerance. Another thing to look at is the expiration date. And I say that because you may still have, depending on your calibration frequency, plenty of gas or liquid left over after the expiration date. And so you have 2 options. One, you can dispose of the cylinder, but another option is that you can talk to your standard provider and go back to them and see if they will recertify the cylinder to what its composition is. And a lot of times they will be able to do that for a nominal fee. And the reason we say you don't want to use it past the expiration date, it's just more of the doubt. If anything goes wrong with a GC and you're getting error messages, even you don't want to have that doubt that there's something wrong with your gas. Because if the gas is wrong, everything from that point is going to be wrong. Your GC will never be accurate. If your gas is wrong, there's no way your GC can be accurate. There's no way you're getting the appropriate readings. So it's good to have a confidence in your gas calibration cylinder. And then finally, in the last box I highlight, this is kind of really gives you some information about the cylinder itself. It's going to give you the pressure, it's going to give you the volume of material, it's going to give you the connection to it as well. It's going to tell you what the unit of measurement is. On this particular one, because it's all gases, it's not giving you, not hydrocarbons, it's not giving us a hydrocarbon dew point. If that was located on that, and which it generally is in our C6 and our C9 certificates, you want to make sure you stay above the hydrocarbon dew point. And the recommendation is 30 degrees Fahrenheit above the hydrocarbon dew point. Again, it's not on this particular one, but if this had hydrocarbons in it, it likely would be there. And you do want to stay above that. Otherwise you end up having dropout. Okay. So one of the questions we got from a previous webinar was, can you store the calibration gas certificates in the GC? So you can see it's only a yes or no. I don't know how many will type answer here below. So that's a slight error in my survey, but we'll see if you guys know the answer. Can you store the calibration gas certificate in the GC? So guys, we'll give you guys a few seconds to answer that. Okay, good. The answer is yes. You actually can store it into the GC. So, and this is another question. You can store it. Basically, you would go where the parameter sheet is, click on it, and then when you basically you have the chance to upload it. As long as it's in a PDF, Word, or Excel file, you can definitely upload it. And that works for our XA series. So that's the 370 XA, the 700 XA, and the 1500 XA. Here's another question. Yes, no, it depends. If you have basically had a calibration gas and it got below its hydrocarbon dew point, can it be brought back to its original mixture or blended? I'll give you about 30 seconds to answer that. I've been trying to answer while you guys do the poll some of these questions, but looks like I'm falling behind. So hopefully you guys can answer this, and we'll see. So you're right, and it's a depends. And the reason it can be a no if the calibration, why it was below temperature, was operated or gas was taken out, why it fell below its hydrocarbon dew point, then no, it cannot be brought back, because what will happen will be that the lights came out and the heavy stayed behind, and so therefore now it's not a known standard, and you don't know what you have. And if your calibration standard, if you don't know what's in there, it can't be used to calibrate the GC. It's a yes if it went below, say, the temperature and it was in storage. Then you could heat it back up and blend it, and take a bit. We say overnight, but get it back up to temperature. So long as it was not open, why it was below the temperature, then yes, you can remix it or have it back to what it says. But if it was opened during that time, it was below the temperature, or it was used, or any gas was taken out, then no, it has to be disposed of. You now no longer know what's in there, and it's no longer a standard. Okay. I do want to just point out quickly the difference between a liquid and a gas calibration standard. And the reason we do this is because this really affects whether we do an auto calibration or a manual calibration. And a lot of times when we do talk about calibrations in a lot of the classes we do really reference more at being a gas. It's so much easier to calibrate with a gas than it is a liquid, to be honest with you. It's also a little bit cheaper. So there are some differences, and it really has to do with the property of the standard, or liquid versus a gas. So the gas cylinders are pretty large. If you've ever been to our facility or in your own facility, they're pretty good size dimensions. They could be 24 inches wide by 40 some inches or greater tall, whereas the liquid cylinders are really this kind of maybe a 2 feet long, almost looks like a spot sampler type of concept, significantly less volume. And it's really that less volume that they contain. One of the reasons we don't do auto calibration with a liquid. The gas, there's plenty of it there. Again, we're really are doing with the properties of the two different materials, a gas versus a liquid, that really affect that. Also the pressure. For the gases, it's the higher pressure. So more volume, higher pressure, you're really not going to use a whole lot of calibration gas or standard when you're doing your calibration. Liquid, on the other hand, it is possible that you may go through that full 0.8 liters. May need another, when you're doing your calibration. So that's another reason why we again reference it, that it be more mechanical, so that you can also watch it. You're also going to watch about the pressure, the head pressure, right? Because you do need pressure within that cylinder to make sure if there's any light that they stay within a liquid form. So it's a bit more complex of a system when you're working with the liquids than working with a gas. And so we just want to point that out. Okay. So this is now where we get really, unfortunately, good or bad, specific on how to auto-calibrate with our gas chromatographs. Again, I do think it's a similar process with one of our competitors. Again, I'm really more referring to online type of GCs. So for us, if it's a gas and it's auto calibration, and this is really what you would do for both, whether it's a gas or a liquid, is that you would go into Armand 2020, go under Applications, click on Streams. And I do want to reference that somebody did ask us once, why would you want to auto-calibrate? And really the simple answer is one less thing you have to remember to do in your life. It will do it for you. Again, it works great when it's a gas, but more importantly too, if you have certain requirements. So a lot of custody transfer applications require a daily calibration. Also a lot of refineries, there could be certain rules require a daily calibration. It's one less thing you have to do if you can have the GC do it for you. So again, the same way you set up a calibration stream is the same way that you set up a sample stream. So this is what the screen should look like. And so the first thing you look under is usage. You really basically have, you either pull down analytical, which is basically for a stream analysis, or cal. So you're going to want to select cal. And so if you look here in this particular example, this line 2 is marked as the calibration stream. And so then from there, you're going to want to select the appropriate component data table to associate with it, as well as the time event table. Now this is what you'll do, whether it's a mechanical calibration or a liquid calibration. These first 3 steps apply to both. The next step, where you check the auto box, that's only for auto calibration. Once that box is checked, then the start time field and interval field will be available to write in. Otherwise, it will be blued out. And so that's really the step. Step number 4 is the one that kind of distinguishes between whether it's going to be an auto calibration or a manual calibration. If it's whether it's in steps, I should say step number 5, number 6, applies again both to manual, as well as auto calibration. And so that you can enter the number of total runs, and so that's the number of times the GC will perform analysis against calibration. That can be anywhere up from 1 to 10 runs. The average runs, that can be anywhere again from 1 to 10. And the average runs is basically it's the number of the most recent calibration runs to average. So in this particular example, if we say 3 calibration runs are to be performed, and the average runs is 2, then the last 2 runs of that 3 will be averaged together for the calibration results. 3 and 2 is the default value when we ship it from our facility for gas samples. You can obviously go in and modify that if you want. So step 7 and 8 are specific to auto calibration. You can put in the start time, and then your interval can be anywhere, basically, or I should say the max, because it could be anywhere from an hours from like basically 1 hour all the way up to 999 hours or 41.5 days. You can have the interval be, and this is adjustable. So basically, there's 8 steps. 5 of the 8 steps apply to both mechanical, I don't know why I keep saying that, to manual as well as auto. So there's just a few specific steps for auto, and that is basically clicking the auto box, as well as inserting the number of start time, as well as your interval, how often you want to do calibration. And most are basically our pipeline applications, it's 24 hours. So that was the easy part. It's very straightforward, 8 simple steps to get done. I'm going to see if there's any quick questions. I'm going to look at this one. How frequently should we validate or calibrate a GC? So in that particular question, for calibration, it's whatever your requirements are. We're not going to tell you what that is. So pipeline custody transfer applications, most of the tower specifications say 24 hours. I will tell you for some of the EPA requirements, the calibration will tell you 24 hours on the mid-level, and then for the low, medium, and high, you have to do that calibration on a quarterly basis and submit the data. So it's whatever are your basically legal requirements that you have towards your customer or what your company has specified. So we're not going to tell you what your calibration requirements are. We do know there's plenty of applications where people may do it once every 30 days, only upon noticing of an error. So it really depends on your application and what your requirements are of your company, as well as any legal requirements that you need to meet. In terms of Validate, we do have a webinar on that, and Validate is a little bit different from Calibrate, because with Calibrate you're changing the information related to the response factors. Validate, you're just kind of double checking to make sure the GC is functioning accurately and appropriately. And we do tell people to validate every 30 days to double check that out. So it's a little bit different. Validate, you don't change the response factors. You don't do all the purging. It's just a little bit different in terms of your checking to make sure everything is working appropriately. So that is up to you guys how and the time frequency that you want to do that. I'm trying to see if I can get another quick question in. Is the expiration date 5 years for a cal blend? So that was one of the questions, and yes, so that Emerson doesn't get to decide that, and that is the calibration standard manufacturer. Some we've seen 5 years, some we've seen a year. It really depends on what's in that calibration cylinder and what you're asking for. So that is basically based on the recommendation from the calibration gas or liquid standard manufacturer. Emerson has no input onto that. Okay. So it's a slightly different when we do a manual calibration, whether we're going to do a gas or a liquid. So this particular one, where you're going to do, I'm showing you as a gas. So you'll go in under Control, select Calibration. Then the next screen is going to come up, and you're going to select Calibrate. We recommend that you Purge, as well as mark calibration type as normal. And normal basically means the stream will be updated with the calibration data unless the data is outside the accepted deviations. Okay. Oh, here we go. So why purge for 60 seconds? So the reason you do that is you want to make sure, when we talk about we purge when we do the sample streams, well, we're purging for the calibration stream as well, because you could have in that tubing any remaining gas, or it can be, if the time has passed, it could be air has gotten in there and all. So you really want to kind of like sweep that all clean. And as we say, you really want fresh calibration gas, because that is what you're going to use as your reference moving forward. So you want that to be good, clean calibration, fresh calibration gas. You do have the option, if you want to modify the purge stream time. 60 seconds is the default, but you can set it up to 600 seconds. Generally, in most applications, those 60 seconds of purge is appropriately. People do ask occasionally, what is forced cal and can I force cal? So forced cal is very similar to normal calibration. The difference is, and it's a critical difference, is that the component data table will be updated with the calibration data even if the data is outside acceptable deviations. So basically, if you force cal and there's something wrong, you are basically telling the GC, overwrite what's wrong, ignore it, and take my numbers. That said, we don't agree with doing forced cal because it inhibits the alarms, and therefore it's hiding what something is wrong. That said, there are times that forced calibration is acceptable. We'll give an example later on in the presentation, but say you had repaired the GC, so the old calibration, the scenes are not going to match. Maybe we did valve timing or whatever. You could end up having to do a forced calibration because you are going to alarm because you made some changes that could shift your retention times. So you will get the alarms, and that's fine to do force cal in that particular example because you know why it's alarming. As long as you understand why it's alarming, then it's okay to do a force cal. But if the only reason you're doing a force cal is to eliminate the alarms, that's not a good reason, and it's going to impact you greatly because obviously if your calibration is wrong, the calibration helps us determine the response factors, which help us determine the string composition. So it just goes downhill from there. Okay, so we want to confirm we have a good calibration, so we want to verify there's no alarms. We will generate a final calibration report, and then we will confirm that response factors are in order. And so I'm not going to go into everything we went through last webinar on response factors, but I am going to show just a few slides from that webinar because response factors are so critical in determining that your GC is operating correctly and the calibration has been done correctly. So here's the final calibration report that we went over last month during the response factor report. But there's a couple things that are important to look at in this particular thing. So the calibration concentration, that first column should match your certificate. And then the new response factors. This is a TCD application, C6 Plus. We want these response factors to be in order of the thermal conductivity of the component. So you'll notice the components are listed in the order that they eluted out, but we want the response factors to be listed in the order of the thermal conductivity because that's the detector. In this particular case, we know everything looked good because of the asterisk, but we want to verify that. So if I get to the next slide, you will notice the methane has the lowest thermal conductivity. It also has the lowest response factor. And as we go one and one all the way up through the components, we see that there is a match. So in this particular case, this is very good. That gives us the heads up that we know things are correct. We could feel confident about the GC calibrating correctly. Well, also what we talked about last month was that you could also plot the response factors, and that would tell you if things were doing correctly. In this particular case, the reference would be how the GC left the factory, and the latest would be the calibration run that was just done. So in this particular example, everything looks perfect, looks really good, so we can have confidence in our response factors. Again, if anybody has any questions, I definitely recommend you attend or listen into the webinar that was done last month on response factors. It is on the Emerson website for those who have an interest in that. And just a reminder as well, the same theory works for if things were done with a FID. FID's a little bit different. It's a mass detector. So instead of looking at thermal conductivity, we are looking at the number of carbons. And so in this case, we would expect the number of carbons needs to align with the response factors. And in this case, this one looks good as well, and we would accept the response factor order and say this looks good. Again, if anybody needs to know the link to that, to last month's webinar, you can contact us, analyzers@emerson.com. Okay, so liquid, which is basically a bit more complex than the gas. In fact, there's going to be a couple of reasons, and we'll go through it. So it's slightly different. So with the gas, when we went in under control, we went to calibration. This time, we're going to go under control, single stream. And then we're going to select, when that second screen comes up, we're going to select the calibration stream. Again, we're going to click Purge, and we're also going to click on continuous sequence or continuous operation. The Purge does the same thing for the liquid as it did for the gas, and basically it's going to purge for 60 seconds. It's going to clean out the tubing. But you will find that in most cases, purging for 60 seconds is not going to be enough. Hence, why do we go continuous operation? Because you're going to need it. And I know that sounds kind of flippant, but it's really kind of true. It literally can take up to 10 to 15 runs till you get a stable reading. And the reason is, if you think about the properties of a liquid versus a gas, so you have the liquid in there, and so your point from basically the calibration cylinder to basically the vaporizer, you can have a liquid in there. When that liquid is vaporized, it can go to 400 to 600 times that volume. All that old, basically liquid calibration standard, has to be purged all the way through the system. That takes a bit of time. So you've got to kind of flush that all the way through it. So that's why you can be doing the runs so you start seeing stable values. So that's why I said, again, this is also why it's more mechanical, or manual, I should say, because of that. Why we don't automatically. Also, you want to verify you have the correct head pressure, because that's going to tell you whether any of your lights have basically flashed off. You need to do that. A lot of times there is basically a header of helium that helps keep the pressure within the cylinder so the lights stay within a liquid form. Again, so many runs. Air ingress could also apply to the gas, but something that's really specific to the liquid is the volatilization. It is possible to fractionate your sample. So that's basically the lower gases boiling off first, so you're getting a mixture of gas and liquid. So you're basically not getting a mixture that was basically your calibration standard. So you want to make sure that's not happening. And then stratification, just over time, your liquid cylinder will stratify. So you definitely want to make sure it's mixed. I know some of our customers have almost like paint can shakers to keep their liquid calibration gases all mixed in. But you're definitely going to want to have that mixed before you start pulling out liquid out of your cylinder, because then you're going to get the stratification, and once you pull it out, it's already been stratified, you no longer know what's in your calibration standard, and if you don't know what's in your calibration standard, it can't be used as a calibration standard. So just keep that in mind. So this is one reason why we commonly run the results multiple times. So with a gas, it tends to be 3 times our standard. With liquids, we are going to run the thing as a stream first so that we get some stability. So then the next question is, well, how do I know when I'm stable? Basically, you're going to have the chromatogram viewer up. It kind of helps with that. Also be looking at the data of the chromatograms. You're going to watch it to see that the repeatability of when you keep the runs are within the specification, but also that there's not really a big shifting of the components. You're not seeing a trend up or a trend down. You want to see when it's basically you're getting the same result time and time again. When it is stable, this part aligns very much to what it was if it was a gas and you were doing a manual calibration. So you would go in, you have the stability, you go in, you do the calibration, you select the calibration stream. Again, you would still do the purge, you would select normal, and the same steps again, verify no alarms, generate a final calibration report, and confirm the response factors are in order. And I just want to remind you again, back when we set up the streams, that calibration stream, when this runs the calibration on the liquid, whatever you set up as the number of streams to run, so say that in our example was 3 and 2, it will do that when it does the calibration. So you'll have your previous runs when you're running it as a stream for stability, and then when you go to calibration, it will do whatever you select as the number of runs, and then the average runs. It will do that as well. So just keep that in mind. So that also then leads me to the next thing, that when I was talking to our technical services guys, because this liquid cylinder is smaller volume, that they tend to want to make sure before they hit the calibration stage that they actually have it's steady. And so what they'll do is that once they believe it is steady, and this is where we say you never do this, but now I'm telling you to do it, from the viewer screen, they hit the force cal. So that basically replaces, as I told you before, when you hit a force cal, it overwrites the previous response factors. When they feel it steady, they will hit a force cal. They will check the response factors and the component concentration. So everything you do when you run a normal calibration, they will check this. Make sure it makes sense. So do the same thing again. If it's a TCD, checking the thermal conductivity order. If it's a FID, checking the number of carbons order. And they'll check if everything looks good. If it does, then they will run a calibration run that we just talked about, and then compare both the forced cal and that calibration run. They will compare the chromatograms, they will compare the data. So this is an example that was done, and you can kind of see the bottom, the red and the blue was the forced cal, the purple and the green was the calibration. And they will look at them to make sure they align. And the reason they do that is that the liquid is A, expensive, the liquid standard is expensive, and two, there's not a lot of it, so they don't want to keep running calibration streams where you're doing the 3 and 2 and the purging if they don't have a high probability of passing calibration. So they will do the runs when they think they're steady. They will do a force cal off the chromatic viewer screen. That validates and that looks good to them so they can have the response factors. Then they will turn around and do the calibration steps that we just mentioned, and then they will compare the two. And that's how they will do a liquid comparison. That's how basically our tech service guys does this. There are just a few features on the calibration that I would just want to quickly mention. So if you wanted to do them, they're under our systems screens. There's basically 4 of them. So Chromatogram archives, this is basically, you have 2 options. You just want to save the last one of the day, or if you want to save them all the final calibrations. You can also then, if you fail calibration, you can actually have, instead of just the GC, give it another shot to pass. And also repeatability, so even if you pass, you can turn around and say, hey, I just want to double check, even after you say everything's good on the first run, do it again. So that option is there. And then I think I mentioned previously that you could change that purge duration from 60 seconds, which is the default, to 600 seconds. So it would be under the system screen that you would scroll down, and you could write in what you want the time to be. Again, the default is 60, but you can change that to what you want it to be. I do have some previous questions. I'm not going to read them to you. In fact, I might try to actually instead, in the last remaining minutes, try to answer some of the new questions we have. But these are some ones we've gotten before, and this will be in the presentation. I will also tell you in the presentation, which I knew I wouldn't have time to cover, is if you are changing the calibration bottle or cylinder, the procedures to doing that. And that's in this presentation. It's not covered here today for time limitations, but I do have it in the PDF version of this. So if people want to know the correct procedure when you're changing out a calibration bottle to make sure that, again, you're getting very stable data before you calibrate with it, we do have that procedure outlined in the PowerPoint that we'll make available to you guys. So I'm going to see if there's any unanswered questions. Actually, it looks really good. It looks like everything I'm showing is that there is no unanswered questions, which is good. So I guess we will be able to close it a bit early. We're about 5 minutes ahead of schedule. Again, if you guys want a copy of this presentation as well as the product notification that outlines the calibration certificate standards that we recommend for C6 and C9, you can just contact us at analyzers@emerson.com. And with that, I will give you 5 minutes back to your day. Thanks a lot, guys.